this, I want to get, it might take me a little minute to get screen share going, so let me get that set up. Hopefully this will work. All right. Got my pen here. It's all right, I'll get another one. All right. Let's enlarge this. Let me grab my pen, still have a minute or two. Ouch, that hurts. Okay, this is what they call a tabula rasa. It means a blank sheet. So carte blanche means a blank sheet too, but it has different meaning. Carte blanche is means an empty check. You can write it for any amount you want, whereas a tabula rasa means like a school blackboard or something that's been erased. So whatever was on it before has been removed. So it's like there might have been incriminating stuff on it, but it's now gone. That's the kind of the idea of it. I learned this because in writing an English paper when I was a freshman, I confused the two, and the teacher, really got on me for it. So I never forgot the mistake. English was not my strong subject. Although my daughter is a natural for it. Okay, so tonight we've got a lot of stuff to do about rotations and operators, and this is going to lead up ultimately, not tonight probably, but next lecture, to the Wigner-Eckart theorem, which is will probably intimidate many of you, but it shouldn't, because it's actually not that hard to remember, and it's quite easy to use for most applications. But there's a lot of theory behind it, and I'm going to outline or make a beginning on outlining some of it tonight. I want to begin with the definition of a rotated operator. Let's talk about a quantum system where we've got rotation operators. I'll let U stand for a rotation operator. We can think of it, parameterize it by its axis and angle, and let's let R be the corresponding classical rotation like that. Let's just use that notation for it. So when it comes to kets, the way we transform kets is we take a state vector psi and we map it into U times psi. And I'll call this, define this to be psi prime. So the prime just means a rotated version of it. So we can just put, say, a U above that to indicate what the operator does. Now, what I'd like to do is to indicate also what the action of rotations upon operators. So we got it for kets. Let's see what it does to operators. The correct definition is that if I have an operator A, it gets mapped into the conjugation by U, UA, U dagger. And we can define this to be A prime, where again, the prime means the rotated version. The reason why we make this definition of the rotated operator is because by this definition, we have the property that the expectation value of the rotated operator in the rotated state is equal to the expectation value of the old operator unrotated in the unrotated state. So in other words, the equation is this, is that psi prime sandwiched around A prime is equal to the psi sandwiched around A. The physical idea of this, if I can put it in physical language as much as possible, is that you have to understand that A and A prime are different operators. I mean, they're obviously not the same operator. And so therefore they correspond to different physical measurements. And the idea is that if I make measurements of the original operator A, and I make measurements of A prime, if I do them in the same state, the answers are going to be different because they're different operators. But if I make measurements of A prime, what we define as the rotated operator with respect to the rotated state, then I get the same answers that I got in the original operator with the original states. So if you think about, like, rotating the system and you rotate the angular momentum vector, then it's kind of clear that's what should happen. All right, anyway, this is the definition that we use. Now then, having got a definition, so let me box it here because this is the definition of the rotated operators, which I think is new for the course. Now, having got this definition of rotated operators, we now use this in order to classify operators by how they transform under rotations. The notion of classifying physical observables by their transformation properties is one that runs throughout all of physics. I mean, we talk about scalars, vectors, tensors, pseudoscalars, pseudovectors, and so on. And these all have implications for how they transform. Sometimes we're not talking about rotations. We may be talking about Lorentz transformations or other types of transformations. But the basic idea of classifying physical observables by their transformation properties is a common one. It runs throughout all of physics, including classical physics as well. So in quantum physics, what we do is we classify operators by how they transform under rotations. And I'd like to go through some of that. The first thing to talk about is a scalar operator. The scalar operator, by definition, I'll call it K, is one that if you rotate it, so I conjugate it by rotations, you get the same operator back again. In other words, a scalar operator is invariant under rotations, and that's obviously why we call it a scalar. Now, this implies rather trivially this condition that UK is equal to KU, which is the same thing as saying that the commutator of U with K is equal to 0. And this is understood to hold for all axes and angles n hat and theta, which are contained inside the U. In any case, that implies this. Now, if an operator K commutes with all rotations U, then in particular it commutes with infinitesimal rotations, which can be expressed in terms of the angular momentum. And so this implies, and is implied by, the fact that the angular momentum vector commutes with K. That's equal to 0. So let me box these. So there's a whole chain of equivalent definitions of a scalar operator. Let me box the two at the end of the chain here. The upper one tells how K transforms under finite rotations, and the lower one tells about its commutation relations with angular momentum. They both are useful and they're completely equivalent to one another. All right, so that's the case of scalar operators. By the way, the most important scalar operator in practice is the Hamiltonian for an isolated system. It's invariant under rotations because the energy of the system doesn't depend on the orientation of the system if it's isolated from its environment. That's the physical logic of it. So we pay a lot of attention to scalar operators because of this important class of Hamiltonians. I'll come back to that later on in this lecture. All right, the next thing we want to define is a vector operator. So a vector operator, let me call it V, we call it a vector operator, but what it really is it's a vector of operators. You can arrange them in a column if you want, V1, V2, and V3, but each of the components, or Vx, Vy, and Vz, I don't care, but each of the components is by itself an operator. And the condition on the definition of a vector operator is the following, is that if I take a vector operator, I'll write it in terms of all three components, and I conjugate it by rotations. It's the same thing as taking the classical rotation inverse, multiplying onto the rotation of the vector operator V like that. Now, the reason that we make this definition of a vector operator, this is the definition of a vector operator. I'll play with the definition in a minute, but first let me motivate where it comes from. It comes from the requirement that if we have a vector operator and we form its expectation value, let's call it with respect to an unrotated state, and then we compute its expectation values with respect to a rotated state, it's physically plausible that the expectation value, which is of course a vector of C numbers in the rotated state, should be the rotated version of the expectation values in the original unrotated state. So in other words, I should put a rotation matrix there multiplying this. What I mean by R multiplying this is that this matrix element is a matrix element of three operators. And so when you take the matrix element, it just turns into three numbers. So this matrix element here represents, in effect, a column vector of ordinary C numbers, and that's just multiplied by the rotation matrix R. But in any case, given that psi prime is equal to, it's given up here in terms, where is it? Given up here in terms, it's U psi. This left-hand side is the same thing as psi, U dagger, V, U psi, like this. I'm doing this in a box because it's a digression. But if we compare the two sides of this equation, the psi is arbitrary, and so that gives me U dagger V U is equal to R times V. Or if I swap U and U dagger, I have to swap R and R inverse, and then I obtain this definition, which I started with by citing just a moment ago. This is one fairly convenient form for the definition of a vector operator. Now then, this is a definition of a vector operator. Oh, by the way, in case this notation is not completely clear, let me write it in component form. If I take one of the components of the vector operator, vi, and I conjugate it by u, now R inverse is the same as R transpose. So the right-hand side can be written as a sum on J of Vj multiplied times Rji. And I'll write it like that. This is in a completely equivalent form, more explicit form of the transformation property of a vector operator, but written out explicitly in terms of components in case that's confusing, which it may well be. All right, let's see here. Let me get a little more light here on my paper. Maybe I can do this also, lighten it up a little bit. Oops, sorry. Oh, nope, that was wrong. Okay, excuse me a second. I've got to restore the technology here. Let's get this here. Port photo. Let's get it here. Flip it. Oh, nope, I didn't mean to take a picture. I want to flip it. Nope, I keep taking pictures. There we go. These pictures are stored somewhere in my iPad, and I don't know where they are because frankly, I don't know how to use an iPad. All right, let's see. Let me lock it in. Let me lock it in. All right, good. Now, all right, now, turn this down a little bit like that. All right. Okay, so that's a definition of a vector operator. Now, just as we did with scalar operators, you can get an equivalent version of this definition expressed in terms of infinitesimal rotations. That's essentially what these angular momentum commutators are. So to do that, what we do is we'd assume the angle was small, and we write the u operator as 1 minus I over h bar times theta times n hat dotted into the angular momentum vector j, like that. That's the infinitesimal version of a rotation operator. And for the classical rotation, we write it as identity plus theta times n hat dotted into these script j vector of 3 by 3 matrices that we talked about before. And if you plug that into this equation here, and then plug the r in the right-hand side, and you go through the algebra, what you will find is that you get a commutation relation that looks like this, is that ji commutated with vj is equal to ih bar times epsilon ijk vk. And the derivation, that's straightforward, and I'll omit it, but it's spelled out in detail in the notes. I do want to say, however, that these two versions of what amount to being a definition of a vector operator are completely equivalent to one another. One of them specifies the other and vice versa. One is basically finite rotations, and the other involves infinitesimal rotations. So a lot of books would define a vector operator in terms of its commutation relations with angular momentum, but I think it's important to see how it's related to conjugation by rotations as well. Okay, so that's just the definitions. Let's talk about some examples of vector operators and see what we can do about this. By the way, once you've got this definition of a vector operator, there's all kinds of little theorems that you can prove, which are actually rather obvious. One says that if I have two vector operators, v and w, let's say both of them are vector operators by this definition, then the dot product of v dotted into w is a scalar operator by the definition up above. And the cross product v cross w is a vector operator, is a vector. That can also be proven, straightforward proofs. Another property is that if I have a scalar operator, let me call it f, and I multiply by a vector operator v, I get a vector. All the things you'd expect just on the basis of ordinary C number vectors, apply. Basically the theorems go through. One thing to pay attention to, however, is that in the case of operators, they of course don't commute with one another in general. So v dot w is not the same as w dot v, and similarly v cross w is not the same as minus w cross v, which it would be for C number vectors. You have to be aware of that and be careful about that when you're doing calculations. All right. In any case, there's these little theorems that come up. Now, how about some examples of vector operators? If we take it depends on the system, of course. let's take the system where we've got particle moving in 3 dimensions. So the Hilbert space is a space of wave functions in 3D like this. Let it be a spinless particle for simplicity. It would be fairly obvious or fairly logical that the position vector should be considered a vector operator. But if we want to see if it is according to the official definition, we need the angular momentum. Well, the angular momentum for this case is L. We call it L instead of J. And of course, it's X crossed with P, like that. And so, so X is a vector operator if the commutation relation LIXJ, if this commutation relation holds, LIXJ is IH bar epsilon IJK XK. And this is a commutation relation that you can check by just plugging in the value of X cross P for L and just working through the commutators. In fact, you may well have done this in your undergraduate course. So if you do this, you check this, and this then shows that X really is a vector operator. You can do the same thing with the momentum. And again, it's just a straightforward calculation, and you'll find that LIPJ is IH bar epsilon IJK PK, thereby proving that the momentum is also a vector operator. Then in view of our theorems up above, this implies that X crossed with P, which of course is L itself, is a vector operator. And therefore that implies that the commutator of Li with Lj is equal to IH bar epsilon IJK LK. Well, this last commutation relation is of course the standard angular momentum commutation relations that apply for any angular momentum. And the point is this is now emerging as part of the the structure of the theory of scalar and vector operators. But there's another interpretation for this. It's not just a commutation relation. It's making a statement that the angular momentum is a vector operator. More generally, on any system, we have an angular momentum vector J, and its commutator Jijj is given by IH bar epsilon IJK JK, because that just comes from the commutation relations of rotations. But this means in particular that the angular momentum vector on any system in which angular momentum is defined is officially a vector operator according to the definition that we've given. All right.
Can we have vector operators in higher and lower dimensions as well?
When you want to talk about classifying operators according to how they transform, you need to specify what the group of transformations is that you're talking about. So in some contexts, you might want to use Lorentz transformations. In others, you might want to use rotations in higher or lower dimensions. So to answer your question, it would depend on what the class of transformations is that you're talking about. But yes, you could talk about in 2D, you could talk about how they transform under 2D rotations. The definitions would be straightforward generalizations of what I've done here, and similarly in higher numbers of dimensions.
Okay, thanks.
Okay. Okay, so one of the things that theoretical physicists spend about half their life doing is figuring out how things transform under various kinds of transformations, and those exercises are all generalizations of what we're doing here. Weinberg, in particular, his books are I'm exaggerating, but they're like 90% filled with working out transformation laws. So how does it transform? All right. Anyway, so that takes care of vector operators. Let me say something about tensor operators. A tensor operator is a vector operator is a collection of 3 operators that have certain transformation properties. A tensor operator, which I'll call Tij, this is a tensor operator in what we'll call Cartesian components. A tensor operator, a second rank tensor in Cartesian components, is actually a collection of 9 operators that transform this way. Is that if I conjugate one of the components with a rotation operator, what I get is a linear combination that looks like this. It's a sum on K and L of TKL, and then I have RKI and RLJ. And let me box that because that's the definition of a tensor operator. And I hope you can see that it's a generalization of the definition of a vector operator, which is in this box right here. There's just one copy of R for a vector operator because it has only one index, and for T there's 2 copies of R. There's one for each index, and the way the rotation matrices are used is follows the same pattern. Okay, so we'll take that as a definition of a tensor operator then. Now let me give you an example of a tensor operator. One of the most important in practice is the quadrupole moment tensor. If we have a collection of charged particles that have charges Q alpha and positions X alpha like this, alpha equals 1 up to some number of charges, then these charges possess a quadrupole moment, which I'll call Qij, and it's given by the sum over the particles, alpha, times the charges Q alpha, and then we multiply this times the quantity 3 X alpha I X alpha J minus delta Ij times R alpha squared. And the reason we define the quadrupole tensor operator in this way is that, well, this is a quantized version of the quadrupole tensor that appears in classical electromagnetism, like in books like Jackson, and it gives the second order correction to the interaction of a distribution of charged particles. Excuse me, I forgot what I said a moment ago. Let me say it right. It gives the second order energy of interaction of a collection of charged particles in an external electric field. The zeroth order contribution is just the Coulomb potential. The first order correction involves the dot product of the dipole moment of the charge distribution with the electric field, and the quadrupole moment tensor involves a contraction with what is essentially the gradient of the electric field. So you sample higher and higher gradients of the potential as you go to higher and higher ranks of the operators. In any case, this is all stuff that's covered in classical E&M, but since the positions of the particles are operators, this now becomes an operator. So one of the places where this gets used is in the case of a nucleus. In the nucleus, the neutrons don't have any charge, but the protons do. So this sum is taken over the proton charges, and these are the proton positions in there. And so depending on the internal state of the nucleus, you get this energy of interaction as quadrupole moment interaction. And this is detectable experimentally, and this gives information about the structure of the nucleus as well as of the atom or molecule in which the nucleus is located. It's important in applications like that. Now, up here I spoke of a quadrupole, I spoke of a tensor operator, Tij, as it basically is just one that has two components like this, and therefore two indices, and therefore 9 components. But an example of such an operator is a tensor product of 2 vectors. If I have 2 vector operators, let me call it V and W, both of which are vector operators by the earlier definition, and I just multiply the components Vi times Wj like this, then I do indeed obtain a tensor operator. Now, not all tensor operators have this form, but all tensor operators can be represented as linear combinations of products like this, as you see, for example, in the quadrupole moment tensor, because the positions of this is exactly this form in which the positions of the particles are being multiplied like this. In any case, this is an example of a tensor operator, which is sometimes special example, which is sometimes useful to think about. All right. So that's the story then about scalars, vectors, and tensors, tensor operators. Now I'd like to say something about what's called the reducible and irreducible tensor operators. I want to address that terminology. We've used this term irreducibility previously, but I want to say more about it now. Let me go back to the case of a vector operator. We have 3 components, V1, V2, and V3. And by the definition of a vector operator, if I rotate one of these, conjugated by the U operator, you get a linear combination of all 3 V's. It looks like this. This is the formula from the earlier page. I'm just writing it out again. So if we rotate any one of these 3 components of the vector operator, we get a linear combination of the same components in which the coefficients are the classical rotation matrix. It's useful to draw our attention to the space of linear operators. The vector space we've mainly been talking about so far in this course, which I usually call script E, is the state space for the system. That's a space it's isomorphic to the space of wave functions. But the operators that act in this space also form a vector space. I won't invent a symbol for it, but it's a vector space because you can add vectors and you can multiply them by scalars. And so it forms a vector space. And in fact, it's a much bigger space than this state space E. Now, the components of a vector operator can be thought of as being quote unquote basis vectors in a 3-dimensional space of operators. Most general vector in the operator in that space would be a linear combination of those three components. And so I'll write it like this: is A1 V1 plus A2 V2 plus A3 V3, if I can get the numbers right. In other words, it's just an arbitrary linear combination of the three quote unquote basis vectors like this. An obvious notation for this is to write it as A vector dotted, do it right, is A vector dotted into V vector, except A here is a vector of numbers and V is a vector of operators. In any case, you can write it like that. And what this is showing, what this formula shows, is that if I conjugate this A dot V, the A dot V is an arbitrary vector, an arbitrary operator, which lies in the subspace, which is spanned by those three basis operators. And if I conjugate such an arbitrary operator, I get another operator that belongs to the same space with some new vector A prime. In fact, A prime is equal to R times A if you work it out. So what we have here is a three-dimensional subspace of operators, of the space of operators, which is invariant under rotations. That's to say, every operator in that space, when rotated, produces another operator in the same space. So this is an example of, so this type of thing happens whenever rotations act on any vector space. I earlier showed you how rotations act on kets, and then I explained how they act on operators. So these are two examples of vector spaces upon which rotations act. And I'm drawing your attention to the concept of an invariant subspace under rotations. All right. Similarly, if we take a tensor operator, it has 9 components. And if we rotate one of the components, we get a linear combination of the other 9. This is a formula, again, I'm just copying down from a KL from a previous page. It's RKIRLJ, like this. We get linear combination of the same 9 components with coefficients that involve the classical R matrix. And so these 9 components, if they're non-zero of the tensor operator, span a 9-dimensional space of operators, which is invariant under rotations, just like 3D space for the case of vectors. Now, if you have a vector space that's invariant under rotations, the question you ask is whether or not it contains any smaller spaces that are also invariant. If it does, we say the original space is reducible. And then the two components, there's the smaller space and its orthogonal component. The two components into which the original space is broken up are themselves invariant under rotations. And one can ask whether they're reducible or not. They either are or they aren't. If they're not reducible, they're said to be irreducible. Well, if they are reducible, then you can break them down into smaller spaces, which are either reducible or irreducible. And you can keep on doing this. And when you get done, what you end up with is a decomposition of the original space into irreducible and the original invariant space into irreducible invariant spaces. And it turns out these are orthogonal to one another. So I'm going to illustrate this for these examples here. So one question is, so here's an example of an irreducible invariant subspace of operators. It's a space that's spanned by a scalar operator. If you have a scalar operator, when I rotate it, I just get K. So if I multiply K by the scalar A, where A is just a scalar, what I get is a one-dimensional vector space of operators, which is invariant under rotations. Now, a one-dimensional subspace doesn't have any smaller subspaces, so it's automatically irreducible. And therefore, every scalar operator spans a one-dimensional invariant irreducible subspace of operators. What about a vector? The formula is up here. Here's the vector operator. There's 3 of them. It's an invariant 3-dimensional subspace of operators. Is it reducible or irreducible? Well, the answer is that it's irreducible. You can't break it into any smaller invariant subspaces. I'm not going to prove that, but it's actually pretty easy to prove. So you get a 3-dimensional irreducible subspace of operators from a vector operator. Now, what about a tensor operator? Let's take a tensor operator, and to be specific, let's suppose it's constructed as the product of a VI times WJ. Let's say it has that form. And we know that if you rotate one of these components, you get a linear combination of all the components. So this gives us a 9-dimensional space of operators. Is that reducible or irreducible? Well, let's consider the linear combination of these basis operators T11 plus T22 plus T33, which is of course the sum of the diagonal elements, or otherwise the trace of the tensor operator like this, is that sum. If the T is this VIWJ, then this is the same thing as the dot product of V with W. And therefore that's a scalar. Therefore, if I conjugate this by U, that is a one-dimensional, that spans a one-dimensional subspace of this 9-dimensional space, which is invariant under rotations. And therefore it is a smaller invariant subspace. In fact, it's irreducible because it's one-dimensional. So this 9-dimensional space possesses a one-dimensional invariant irreducible subspace. That leaves behind 8 dimensions left. And that's invariant under rotations as well. Is it reducible or irreducible? Well, the answer is that 8-dimensional space is also reducible. And we get that by picking out the antisymmetric part of T. So that's T12 minus T21, which is the same thing as V1W2 minus V2W1, which is the same thing as V cross W, the number 3 component of it. And likewise, the other 2 components be 1, 2, 3, 3, 1 minus T 1, 3 is equal to V cross W 3, 1, 2, like so. And there's the intermediate one. So basically, the antisymmetric part of T is generating the cross product of V with W, which we know is a vector operator, and which I just explained it forms an irreducible subspace. So this 8-dimensional space has a 3-dimensional irreducible subspace that splits off, leaving behind a 5-dimensional invariant space. Is that one irreducible, the 5-dimensional space that's left over? The answer is yes, it's irreducible. And so the original 9-dimensional space is split up into a 1-dimensional subspace, irreducible, 3-dimensional, and a 5-dimensional subspaces like this. These are the dimensionalities of the subspaces. The invariant but reducible space is split into a direct sum of 3 invariant irreducible subspaces of dimensions 1, 3, and 5, containing the dot product, the cross product, and the 5 is the symmetric and traceless part of T. So this is how it is with tensor operators and Cartesian components. Now, sometimes some of these components vanish. It turns out for the quadrupole moment tensor that it's only the 5 part is left, the others are 0. That's because a quadrupole moment tensor is traceless and it's symmetric, so the antisymmetric part is 0. The 9, of course, is the same thing as 3 times 3. And you may notice that the dimension count 1 plus 3 plus 5. This is the same dimension count we get on forming the tensor product of 1 and 1 in angular momentum theory, and collecting out of it a 0 plus a 1 plus a 2, where I'm now not counting dimensions, I'm counting the angular momentum values. This is the decomposition we get when we combine angular momentum, 2 angular momentum values of 1. There's a moral in this, which is that one of the things I'm illustrating here is the manner in which ultimately one ends up attaching angular momentum labels to operators, which are descriptive of how the operators transform under rotation. So operators can carry angular momentum quantum numbers just like state vectors can. Let's see. Okay, so that's the distinction between reducible and irreducible subspaces of operators, illustrated with the case of Cartesian tensors as well as vectors and scalars. Are there any questions about this so far before I move on to another topic? All right, if not, then the next topic is the following. I spoke earlier of scalar operators, and I mentioned that the most important scalar operator in practice is the Hamiltonian for an isolated system, which is invariant under rotations for the physical reasons that I just explained. The topic I'd like to address now is the implications of this fact for the eigenvalues, eigenvectors, and degeneracies of the Hamiltonian. And there are strong implications of this. So I wanted to do this by reminding you of some of what was involved in the construction of the standard angular momentum basis, which I'll call SAMB tonight by its abbreviation, which we call gamma JM. And let me just remind you of this construction. The J and the M are the quantum numbers of the operators J squared and JZ, and the basis is an simultaneous eigenbasis of J squared and JZ. If we diagonalize J squared and JZ, we may find degeneracies, as to say, we may find that the simultaneous eigenspace with quantum numbers J and M is multidimensional. And that's the general case, in fact. So let's assume that it's multidimensional. If we take the stretch, I'll call these spaces S sub JM like this. S means subspace and JM labels the quantum numbers. If we take the stretch space SJJ, where the JZ takes on its maximum value, that's just a vector space in the Hilbert space. And if this is multidimensional, and then there's also the S's for the other values of J. There's one that is one just below it, Sj comma J minus 1, where the magnetic quantum number has been lowered. And then there's a whole collection of these taking all the way down to S sub J comma minus J, where M is equal to minus J, like so. And these are connected by raising and lowering operators. The J minus takes you down and the J plus takes you up, like so. This is a picture of the subspaces in the Hilbert space. This is only for one particular value of J. The Hilbert space in general has many values of J, and for each value of J, there's a similar picture like this. Now, when we set up the standard angular momentum basis, we chose an arbitrary orthonormal basis in the stretch space, and we just label them by gamma equals 1, gamma equals 2, and so on. And then we use lowering operators to propagate that basis down to all the lower spaces. And in the process of doing that, we construct the standard angular momentum basis. I'm really just reviewing some material that I presented a couple of lectures ago. So that's a brief review of how we constructed the standard angular momentum basis. Now, however, we have a Hamiltonian in the picture. And the Hamiltonian, because it commutes with U, it commutes with J as well. So J commutes with H. And since H commutes with J vector, it commutes with any function of J vector. And in particular, it commutes therefore with J squared and JZ. So we now have three operators that commute with each other, and therefore they possess simultaneous eigenstates. So instead of choosing an arbitrary basis in these various spaces, let's try to choose a basis that's also an eigenstates of the Hamiltonian. How will we do that? Let's see if I have enough room to do this here. Let me draw the picture again. Here's the SJJ. So since the Hamiltonian commutes with J squared and JZ, it means we can take the Hamiltonian and we can restrict it to the subspace, the stretched subspace at SJJ. And we get a Hamiltonian Hermitian operator on that space, just restricted to that space. That Hamiltonian operator on that space can be diagonalized, and it has a spectrum, energy spectrum. Now, in practice, that energy spectrum may well have a continuous part, a discrete part, and a mixed part. I mean, it could be a combination of everything, just like any Hamiltonian. For the kinds of systems that we'll be considering, that we typically have a continuous spectrum above some energy, and we may or may not have discrete or bound state energies below that. For the sake of argument, let's suppose that for the given value of J here, let's suppose that there is a discrete state in discrete energy eigenstate in this SJJ, and let's call it psi. We'll just draw it here as a picture of psi like this. And so that means that H acting on psi brings out an energy E psi, but it also means that J squared acting on psi brings out JJ plus 1, because it's in the stretched space, and that JZ acting on psi brings out J because it's also because it's in the stretched space. So it's a simultaneous eigenstate of all three of these observables. Now then, if we then apply lowering operators, what we get is we get states that appear in the lower spaces. Let's look at what happens to the eigenvalues when we do this, in particular the energy eigenvalues. We know what happens to J squared and JZ. J squared stays the same and JZ just gets lowered. What about the eigenvalue of the Hamiltonian? So let's look at what J minus does to, no, let's do it this way. Let's take J minus and apply it to psi. Psi here is in the stretch state. Let's apply J minus to it, like that. And let's see what we can say about that state. When we apply the Hamiltonian to it, because H commutes with J minus, this is the same thing as J minus H psi. The H brings out an E, which is a C number, so it's E times J minus psi. And what we see then is that J minus psi is also an eigenstate of the Hamiltonian with the same eigenvalue as it was in the stretch space. And by induction, each of these states that we get by lowering ourselves on down are all of them eigenstates of H, the Hamiltonian, with the same eigenvalue. So what we can say then is that's going to lower the M quantum number, you see, from J down to minus J, but it won't change the energy. So what this means is we get a collection of 2J plus 1 states, which all have the same energy. And therefore, we have a degeneracy of order 2J plus 1. Now then, these states that are created by using lowering operators span what I've been calling an irreducible invariant subspace of Ket vectors, not operators now, which I was talking about a minute ago, but of state vectors. If we were talking about the original gamma JM standard angular momentum basis like this, we know this because if you rotate this, what you get is the sum on M prime of gamma JM prime like this, and the coefficients of the D matrices. This comes from inserting a resolution of the identity. This is how the basis vectors of the standard angular momentum basis transform, and they just mix up amongst themselves. Only the M quantum number gets mixed up when you rotate. So that makes it a subspace, the subspace spanned by them, that makes it an invariant subspace. And it also happens to be irreducible, which I won't prove, but it happens to be so. So I've been calling these irreducible subspaces. This includes, for example, in the standard angular momentum basis, the vectors that are created with a fixed gamma 1 just going on down, because they were constructed just by applying lowering operators. So the standard angular momentum basis defines a collection of invariant irreducible subspaces that are indexed by the indices gamma and J, and the M then is variable. All right. But the point is that now that we've got a scalar Hamiltonian, we have these invariant irreducible subspaces, which are also eigenspaces of the Hamiltonian of a given eigenvalue with a degeneracy 2J plus 1. All right. Now, so the rotational invariance gives us the structure to the eigenspaces of H and the degeneracies. The question is it possible that the degeneracy could be larger than 2J plus 1? And the answer is yes, and it could happen in at least two ways. One of them is that this state psi in the stretched space might be degenerate. So H restricted to the stretched subspace might have a degeneracy. So it might have two states, let's call them psi and psi prime, that have the same energy. And if I lower them both down, then what I get is a collection of pairs of vectors, or if you like, two different irreducible invariant subspaces of the same energy, each of which has 2J plus 1 fold degeneracy. So in other words, you could get a degeneracy within a given J value because of that mechanism. On the other hand, you could have a different J value, J prime not equal to J, and it's got its own stretch subspace, SJJ prime like this, SJ prime J prime like this, or let's say J prime is not equal to J, and you might have an energy eigenvector, let's call it phi in that space, which might by accident have the same energy as this psi up here. And if that's so, then you now got a degeneracy of 2J plus 1 vectors degenerate over here with 2J prime plus 1 vectors that came from a different value of J. So you could have degeneracies that lie not only within a given J value, but also that cross different J values. Those are the two options basically for creating degeneracies that go beyond what's required by rotational invariance. These extra degeneracies don't come from rotational invariance, they come from something else. Could be just accident. All right. So the result of all of this is a theorem, which I think I'm going to state it in words because it takes too long to write it out. But the theorem is this. It says that in any Hamiltonian, which is invariant under rotations, the discrete energy eigenspaces consists of a set of irreducible invariant subspaces under rotations, each of which contributes 2J plus 1 to the degeneracy of the energy level. And moreover, these energy eigenspaces can be chosen to be orthogonal to one another. And they may involve either the same values of J or different values of J. Okay, so that's the statement. Now, what I'd like to do in the next phase of this lecture is to illustrate this theorem by two examples. The first example is a simple one that's exactly solvable, and the second one is a very complicated one about which we know we really can't solve it, that's for sure. In fact, we don't really have even a very good idea of what the Hamiltonian is. What we do know, however, is that it's rotationally invariant, and there's an angular momentum operator that's defined in the Hilbert space, and that turns out to be enough to draw various conclusions. So let's take the simplest case first. The simple case is that of central force motion. In central force motion, J is usually written as L, which of course is the same thing as X cross P, and we change the quantum numbers accordingly. So the stretch space is now going to be, let's call it S sub LL like this. And if we have a vector in this space, I won't label it, but we have a vector in this space, it corresponds to a wave function. You know what it looks like. It's our radial wave function times the YLL of theta and phi. That's what the wave function is for any such stretched vector in the stretched space. Now, if we want this to be also an energy eigenfunction, and we're talking now about central force motion, then we solve the radial wave equation to get what R is for the given value of L. Remember, there's a different radial wave equation for each value of L. Also, remember that the radial wave equation for a given value of L doesn't necessarily have any bound states at all. But let's suppose it does. Let's suppose it has one. Let's call it psi like this, and then it has some energy levels. Let's call it E sub NL. The N is just in case there's more than one level. So this is the setup for central force motion, and it shows how it fits into that geometrical pattern that I was explaining in the general case and on previous pages. So we just lower this by the magnetic quantum number by lowering operators, and we get a collection of 2L+1 degenerate states. Now, in the case of central force motion, let's ask whether it's possible to have degeneracies within a given value of L. Is it possible in the stretch space to find two psis, let's call them psi and psi prime, that have the same energy? I'm speaking now of bound states. Is that possible? The answer is, in central force motion, no, it's not possible. And the reason is because of the boundary conditions on the radial wave equation which is the solution of the boundary conditions in the radial wave function, which is a solution of the radial wave equation. Boundary conditions are that the capital R wave function vanishes at the origin, and that precludes degeneracies, as I've explained in the past. That's degeneracies for a given value of L. Is it possible to have degeneracies among different values of L? Well, for different values of L, you have two different effective potentials. So the radial Schrodinger equations you have two of them, and they're effectively different equations. So the question is, what are the chances that one of the eigenvalues of one of these potentials is going to land smack dab on top of the eigenvalues of another one? Again, this is a topic I covered in earlier lectures. And the answer is that under normal circumstances, the chances are zero that's going to happen. So it's very unlikely for a quote unquote randomly chosen central force potential that you're going to get degeneracies amongst different values of L. Nevertheless, there are certain important examples, of which the most important one is the case of hydrogen, which has symmetry that goes beyond rotational invariance. In the case of hydrogen, it's SO4 symmetry group instead of SO3. The isotropic harmonic oscillator is another example. The two-dimensional isotropic harmonic oscillator is a central force problem in 2D, so it has SO2 symmetry. But it turns out that's not all the symmetry it has. It goes beyond it as actually SU2 symmetry. And for that reason, there's extra degeneracy amongst different L values. So in the case of hydrogen, we know that the energy levels don't depend on the L quantum number. I went over this in some detail, and I gave you examples about how perturbations break that. You have two examples, one being alkali metals and the other being the volume effect. So I'm hoping you've got that concept down. But in any case, there are exceptions to this generic rule, which says that you don't expect degeneracies amongst different L values. In the case of hydrogen notably, you have systematic degeneracies crossing the L values. Okay, so this now leads to what I'll call an addendum to the theorem I stated before. The theorem stated before, since I didn't write it out, I'll remind you that part of what it said is that the discrete eigenspaces of a Hamiltonian, which is rotationally invariant, consists of one or more irreducible invariant subspaces under rotations, each with a given J value, and therefore 2J+1 full dimensional. The addendum says is that with exceptional cases, notably the electrostatic model of hydrogen, very few exceptional cases, we don't expect degeneracies. We don't expect degeneracies either within or between different J values. They're not likely to happen. it's possible it could happen by, and you can, in fact, if you have parameters, you could tune the parameters and force it to happen. So accidental degeneracies in that sense could happen. But with randomly chosen parameters, the probability that would happen is essentially zero. So what that means is for the vast majority of systems in the real world, each discrete energy eigenspace consists of a single irreducible subspace under rotations characterized by a single J value, and therefore 2J plus 1-fold degenerate. And that's the impact of rotational invariance on an arbitrary system, regardless of its complexity. Now, I told you I was going to do a simple simple solvable problem example of this, and then a more complicated one. The simple solvable one was central force motion, which I kind of outlined in a short area on this page. Let me turn now to a more complicated example. I want to talk about the iron 57 nucleus, 57 Fe, which consists of a 57 body problem consisting of 26 protons and 31 neutrons. That is to say, you can think of it, you can model it as a 57 body problem in which the particles are protons and neutrons. That's only a model, however, because protons and neutrons are composite particles consisting of 3 quarks. In addition, there's the fields involved. There's the quark gluon field, which is in there as well. So there are various models of varying degrees of sophistication in terms of understanding the iron 57 nucleus. Nevertheless, it's a quantum system, quite complicated, which has a Hamiltonian. We may not know what the Hamiltonian even is, but we do know that rotation operators act on this system. We do know there's an angular momentum operator, which is a generator of rotations, and we know that it commutes with a Hamiltonian because the energy doesn't depend on the orientation of the nucleus when it's isolated. So we know all those facts. Now, based on what we said, that means that the energy eigenspaces of the discrete eigenspaces of the iron 57 nucleus consist of a single irreducible subspace under rotations with a given J value. That J value can be interpreted in a model in which we had a system of protons and neutrons. It can be interpreted as the grand total of the orbital plus the spin angular momentum of those protons and neutrons, all 57 of them added up using Clebsch-Gordon coefficients and everything to get a final answer for a definite angular momentum value of the final result. And that's one way of viewing this. But nevertheless, it's got an angular momentum value. When we call that angular momentum value, we tend to call it angular momentum value the spin of the nucleus. So for example, iron 57 in its ground state is a spin of 1/2, as we'll see. That 1/2 came by adding up all these 57 particles and their orbital and their spin angular momenta. Okay, now, so I'm picking on the iron 57 nucleus because it is the main actor in the Mossbauer effect, which has some really interesting physics. So I'm going to put some of this mathematical formalism on hold and tell you about some interesting physics for a change. And then to illustrate some of the features that I'm trying to, some of the general points that I'm trying to make here. So let me tell you about the Mossbauer effect. I've always been fascinated by it. The physics that underlies the Mossbauer effect has to do with the emission and absorption of radiation. If we have a quantum system that has 2 levels, let's say A is the ground state and B is an excited state. This could either be a nucleus or an atom or other systems as well. If the system is initially in the excited state, then of course it can emit a photon, drop into the lower state, and the photon has an energy h bar omega, which in a simple description anyway is given by the difference between the energies of the 2 levels, EB minus EA. Now then, so the photon then travels away. Now, if our system has other atoms or nuclei of the same type around, and let's say the others are in the ground state, maybe only one of them was in the excited state. Let's say the others are in the ground state. Then this photon, which is cruising out here now and has this energy h bar omega, it looks like it has exactly the right amount of energy to raise this other atom from the ground state into the excited state. In other words, induce the reverse reaction. And the question is, does that happen? So I'm thinking now in Mossbauer type experiment, you'd have a sample of iron containing some subset of iron 57 nuclei in their excited states, which then undergo decay, emit photons. And the question is, are those photons immediately absorbed by the next iron atom they encounter because they got exactly the right energy to do it? The question is, does that happen? And the answer is no. There's many complications to this little picture that make it more subtle and more interesting. In the first place, the energy of the photon emitted is not exactly EB minus EA. And the reason is the uncertainty principle for energy and time. In quantum mechanics, energy is only defined precisely in the case of a process, it takes an infinite amount of time. But the emission of the photon does not take an infinite amount of time. There's rather the decay time, let's call it tau, for the emission of the photon. And basically after a few multiples of tau, the photon is gone. So the process is over. And what that means is that there is an energy uncertainty, which is a delta E, which is of the order of h bar divided by tau. And this is the uncertainty in the energy of the photon that's emitted. So if I plot the photon, the energy that, so if I let's say have these systems, a collection of these systems, and they undergo these decays, and I measure the energy of the photon that's emitted, then I get a probability for various energies. And the nominal probability, the nominal location for the energy of the emitted photon is EB minus EA. Let's mark that on the energy axis like this. But not all the emitted photons are exactly at that energy. I mean, that would be a delta function. You wouldn't expect that anyway, because delta functions are really non-physical. You'd expect something that's widened somehow. They call this line broadening. And what I'm talking about here is called the natural line broadening or natural line width. So in any case, if you measure the energy of these photons, you get a distribution around this nominal energy of a certain width delta E. And that energy, that width delta E is given by this formula. It's basically h bar over tau. That means the ratio delta E divided by E, where E here is the E is defined here as EB minus EA. This is the same thing as delta omega divided by omega, because just multiplying by h bar converts frequencies into energies. So this is the spread in frequency of the emitted photon compared to the average frequency of the photon is delta omega over omega. Now this is referring to the energies of the photons emitted by such systems. But we also want to talk about the energy. We also want to talk about the absorption of photons. Let's say we've got a bunch of atoms in the ground state, and this stream of photons is now coming through. What's the probability of the absorption of the photon? Well, it's the same delta E. The same delta E applies to absorption as it does to emission. So this is a probability either absorption or emission. In other words, if the incident photon on an atom or nucleus or other quantum system in its ground state, if the incident photon has a frequency which lies within this delta omega of the nominal frequency, then it's very likely to lift the atom into the excited state. But if some physical effect has caused a frequency shift to shift it out of resonance by more than delta omega, then it won't do it, and it won't do anything. It'll leave all these atoms in the ground state. So that would mean in a bulk sample, for example, the photon would just travel right through it and escape instead of being, scattered by atoms that get in the way. Okay. So this is the basic physics of natural line width. Now, are there any physical effects that cause frequency shifts that are sufficient to shift it out of resonance? And the answer is yeah. There's a lot of them actually. There's all kinds of mechanisms for line broadening. One of them is simply a Doppler shift. If the source atom or nucleus, whatever, is moving with some velocity v, then you get a Doppler shift, which is fractionally speaking is v over c. If v over c is greater than the delta omega over omega, then this means the Doppler shift is going to shift it out of resonance. So for example, if the source is moving with a velocity greater than this velocity given by this amount, then the photon that's emitted will not be able to lift the receiving atom into the excited state. Okay, so Doppler shifts will do it. Here's something else will do it too. It's the recoil. Recoil is related to Doppler shift. When our atom or nucleus or whatever emits our photon with energy h bar omega, the photon also carries momentum h bar k. It's really a vector, but let's say it's pointing in some direction like this. This means that the atom, by conservation of momentum, must recoil with a momentum in the opposite direction like that. And therefore the atom recoils with some velocity v. And so the correct statement for conservation of energy is that the initial energy of the system, EB minus EA, for the system that was in the excited state, must be equal to h bar omega, the energy of the photon emitted, plus the 1/2 mv squared kinetic energy of the recoiled emitter. And so what we see is the frequency of the photon that's been emitted is not really h bar omega, it's not really EB minus EA, but it's rather less, somewhat less, because of the energy carried away by the kinetic energy of the recoiling atom. Okay. So this shift in the frequency due to the recoil might be larger or smaller than the delta omega over omega needed to shift out of resonance. It depends on the parameters of the problem. It's different for different systems. Now, this is where the iron 57 nucleus comes in. It's very interesting. The iron 57 nucleus has an energy level diagram that looks something like this. The ground state, let me call it iron just with just the Fe like this. This is all 57 isotope though. Let me call the first excited state Fe plus Fe star and the second one Fe star star. The energy between the first excited state and the ground state is at 14 keV. That's the energy of the photon emitted. It's a rather low energy gamma ray. Whereas this transition up here is more like about 120 something keV. It's somewhat larger energy. Anyway, it's the lower transition is the one that's of interest. The ground state has spin 1/2 and negative parity, so I'll label that. First excited state has spin 3/2 and negative parity. And the next excited state has spin 5/2 and negative parity. And these spins 1/2, 3/2, and 5/2 are the J values of the invariant irreducible subspaces in the Hilbert space of the iron 57 nucleus that represent a given energy eigenstate. It has one and only one, each of these three eigenspaces consists of just one and only one such irreducible subspace for the reasons I explained earlier, is that to go beyond anything beyond, generously beyond what's required by rotational invariance is not likely for a randomly chosen Hamiltonian or a complex one. And that's just what happens here. And here are the J values. Here are the spin, we call them spin, but here are the J values, 1/2, 3/2, 5/2. So this is a subspace of this enormous Hilbert space for this 57 particle system, or more if you include the fields, which has dimensionality six-dimensional space. Here's one's 4 dimension, here's one's 2 dimensions. Okay. Now, this 14 keV photon has the lifetime is about 10 to the minus 7 seconds. And if you combine this in order to compute the delta omega over omega, which is equal to h bar divided by tau times E, where E is 14 kilo electron volts, tau is 10 to the minus 7 seconds, and h bar is h bar. You plug in the numbers, what you get is about, it's about 5 times 10 to the minus 13. I believe that's the correct number. So as a resonance, this has a width, which is something like 10 to the minus 13 times smaller than the energy of the photon itself. It's really, really, really small. This ratio is extremely small. So that means it's going to take only really tiny physical effects, the frequency shifts imposed on this outgoing photon, to shift it out of resonance. So that photon will be incapable of taking an iron atom in its ground state and carrying out the reverse process of lifting it into the first excited state. By the way, iron 57 occurs in natural iron at about the 2% level. So there's plenty of it around. If you just have a block of natural iron, you've got plenty of iron 57 to work with. 56 is the usual usual isotope, and 57 is fairly common as well. All right, now, so it's not going to take anything, any kind of a physical effect to shift it very much. So what about a Doppler shift, for example? How fast would the source iron atom have to be moving in order to shift yourself out of resonance? Well, to find out, we just set this equal to V over C and we solve for the velocity. If you do that, you'll find the velocity is about 0.01 centimeters per second. The speed of light, of course, is very large, but this is an enormous factor. And when I multiply that factor times enormously small factor, when I multiply that times C, I get nothing. That's like, it's basically an ant crawl or less than that. And very, very small velocity was shifted out of resonance. And there are other effects that can shift it out of resonance too. Some of them very small. Some things I call chemical shifts is used for research in chemistry sometimes. Another thing that can do it is a gravitational redshift coming from general relativity produces frequency shifts. So if you have some small frequency shift, which is capable of shifting this thing out of resonance, experimentally, you can compensate for it by giving some motion, Doppler shift, to the source and observing when you come back into resonance. By the way, how can you tell when you're in resonance or not? Well, you have one radioactive source that creates a beam of these photons coming out, and then you've got a block of natural iron here, and you put a detector behind it like this. And maybe the source here, you can attach it to something movable so you can give it some velocity if you want to. So if you're exactly on resonance to this 1 part in 10 to the 13th, then these gamma rays coming in, hitting this block of natural iron, will be strongly absorbed and scattered in various directions, and the detector will detect nothing. But if there's some physical effect that shifts it out of resonance, then these photons will just pass right through the iron block without doing anything, and the detector will detect everything. You'll get a lot of clicks. But if you wanted to find out how much the frequency shift was that shifted you out of resonance, you can compensate for it by giving some velocity here back. And you can put in an oscillator, make it move back, a mechanical oscillator, put in a loudspeaker vibrating, make it move back and forth. And as it does so, when it passes through the right frequency to give you the right Doppler shift, suddenly the detector will stop getting photons. So by doing that way, you can make measurements of extremely small frequency shifts. Okay. So okay, now, but here's the main problem. It looks like the main thing that's going to kill this is what about the recoil effect? So when the iron atom emits, when the iron nucleus emits this gamma ray, it recoils. And so that's going to give a frequency shift. And how does that compare to the very narrow resonance? Well, I'll leave it for you to work out the numbers, but it turns out it's enormously much bigger than the resonance. There's no hope of being able to shift it back. It's not close at all. It's a huge effect. So it would appear that the recoil of the nucleus due to the momentum of the photon is going to destroy this whole process, and you don't have any interesting physics. However, that's not the case. And the reason is because this iron nucleus is not free, but rather it's a part of a crystal lattice. It's connected to a crystal of a large number of other iron atoms. And therefore, one can think of this iron atom as being attached to a system which consists of a large number of harmonic oscillators. Those are the harmonic oscillators are basically the phonon or sound waves in the crystal lattice, like this. So this iron atom is not free. To model its coupling to the crystal lattice in the simplest possible way, let's imagine we have a large mass here. I'll call it capital M, which we're going to let think of going to infinity because this represents the mass of the lattice, and it's connected by a spring to our iron atom like this. So the iron atom is oscillating. Then it's got a quantum number in some quantum. It's got the harmonic oscillator has quantum numbers. The iron atom is in some quantum state of that harmonic oscillator. So now when it emits the photon h bar omega, and therefore is corresponding momentum h bar k is the momentum, and the iron atom receives an impulse from the momentum. The question is, what will it do? The harmonic oscillator, the energy levels in the harmonic oscillator are quantized. Let's suppose that initially, before the photon is emitted, the iron atom is in an energy eigenstate of the harmonic oscillator, call it N, like this. What will the photon do to the state of the iron atom? Well, I think from the homework problem you did the other week, you know it's going to be a momentum operator. It's going to be a momentum operator S of delta P, like this. S of delta P, by the way, is a recall momentum. It's h bar k of the photon, and so S of delta P is equal to E to the minus I delta P times the operator x hat divided by h bar. That's the momentum translation operator. And so this is the state of the system after the photon has been emitted. And if you want to know the probability then of making a transition from state N to N prime, you get it by sandwiching this with N prime and taking the absolute value squared like this. This is equal to the probability of making a transition from N goes to N prime. Now, as you know from that homework, you can make a transition from n goes to n. It's possible to make a transition in which the quantum number doesn't change at all. If that happens, it means that the iron atom did not transfer any energy at all to the crystal lattice. And therefore, all of the energy that is available goes into the photon. And therefore, there's none that goes into the kinetic energy of the iron atom. And therefore, the energy of the photon, h bar omega, is equal to EB minus EA. It is, in fact, on resonance, apart from maybe much smaller effects that can shift the resonance, shift the frequency. Okay. So it's this is called recoilless emission, and it's the existence of recoilless emission. It doesn't happen all the time. There's a probability for it, but for some of the atoms, for some of the photons that are emitted, the emission is recoilless, and that means that you're now sending out a photon which to an extremely high degree of accuracy is at the right frequency for lifting a new iron atom into its excited state. All right, now, that's the basic physics of the Mossbauer effect. Mossbauer received the Nobel Prize for this. The initial applications were to chemical shifts. Extremely tiny effects on the structure of the nucleus due to the chemical environment could be measured by this method. But shortly after he won the Nobel Prize for this, as a matter of fact, the Mossbauer effect was used in what's called the Pound-Rebka experiment. It was carried out at Harvard in 1959. It was the first measurement of the gravitational redshift of photons climbing in the Earth's gravitational field. So basically, they had a transmitter and receiver, Mossbauer photons, in which the transmitter was at ground level and the gamma ray beam was pointing upwards. As those photons climbed in the Earth's gravitational field, they underwent a redshift. The receiver was on the 5th floor or something of the physics building there. And by moving the receiver, giving it some velocity, a Doppler shift in effect, they were able to measure the redshift and climbing up in the gravitational field. And of course, it agreed, naturally, it agreed with Einstein's predictions. But anyway, this was the first experimental verification of the gravitational redshift. Nowadays, the gravitational redshift is routine. Atomic clocks are accurate enough, you can see it. I mentioned it earlier in terms of atomic clocks on satellites. Of course, a satellite has quite a bit larger gravitational potential difference than 5 floors of the physics building at Harvard, so it's an easier effect to detect. Okay, that's basically the physics of the Mossbauer effect, and I brought it up because I wanted to tell you about energy levels of atomic nuclei, what their spin quantum number means, and how it fits into this general theorem about energy levels of systems, isolated systems. A further remark to make here, by the way, is that when we were talking about spins and magnetic fields, we just simply declared that the Hilbert space for the orientational degrees of freedom of the spinning particle was a single irreducible subspace under rotations characterized by a spin quantum number, which was just fixed and characteristic of the particle. Well, if our particle is an iron 57 nucleus and we're doing a spin precession on that, that's just what we've got. It's got spin 1/2. We've got a single irreducible subspace under rotations. But look where that subspace came from. You might say it's the entire Hilbert space for the orientational degree of freedom of the nucleus, but that's not quite right. What it actually is it's the ground state Hilbert space of this much larger, enormous Hilbert space of a 57 particle system, or even bigger if you include the quark gluon field and everything that's in there. It's a subspace of a much larger Hilbert space. The reason we can get away with talking about just that subspace and not the others, like the excited states of the iron 57 nucleus, is because they're separated by nuclear type energies, which, for example, here's 14 kilo electron volts. That's fairly small by nuclear standards, but is much, 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 much larger than the energy of interaction of the ground state spin in a laboratory magnetic field by many orders of magnitude. So there is essentially zero coupling to these higher states. And that's why the Hilbert space for the nucleus is described, the orientational Hilbert space anyway, is described by a single irreducible subspace under rotations. Okay. This ultimately explains also why the spin is proportional to the magnetic moment, and that you will see that coming up in a homework problem in a little while. Okay, so that's all I want to say about Mossbauer. I hope that was fun. Any questions about that? If there's no questions about that, then I want to move on to the next topic, which is going to be the Wigner-Eckart theorem, working up towards it anyway. I want to start this presentation of the Wigner-Eckart theorem by telling you about what I call the spherical basis, commonly called that spherical basis. The spherical basis is a set of basis vectors in ordinary three-dimensional physical space. And what I'm going to do is first define the basis for you, and then I'm going to show you what it's good for, and then I'm going to explain what the deeper significance is. So the spherical basis is three vectors I'll call E1, E0, and E minus 1. They're indexed by an index, as you see, runs from 0 and plus and minus 1. E1 is equal to minus x hat plus I y hat divided by the square root of 2. E0 is z hat, and E minus 1 is x hat minus I y hat over the square root of 2. Excuse me. As you can see, the spherical basis vectors are complex vectors, whereas what I'll call the Cartesian basis vectors are just the usual ones. I'll call them as C's. C1 is x hat, C2 is y hat, C3 is z hat. Those are, of course, real vectors, and so the components of a vector that has real components in the components what would you normally call a real vector in Cartesian components are real, but in the spherical basis, the components are going to be complex numbers. All right, anyway, that's the definition of the spherical basis. Now, the main property of the spherical basis that's interesting to us is the orthonormality property. If I take EQ, Q is an index here I'll let run from 0 to plus and minus 1. So it indexes the E vectors. EQ complex conjugated dotted with EQ prime is Kronecker delta QQ prime. These vectors are orthonormal, but you have, since they're complex, you have to put a complex conjugate on one of them when you take the scalar product. But they're orthonormal in that sense. They're also complete in the sense that if I have a vector x, an arbitrary vector x, I can write it as a sum on Q of coefficients I'll call x sub Q times EQ complex conjugated. And if I do this by forming the scalar product, what we get is that x sub Q is equal to EQ dotted into x, like so. So in other words, I've expanded an arbitrary vector as a linear combination of the spherical basis complex conjugated. You might wonder why I didn't expand them in terms of the basis without the complex conjugate. And the answer is I could have if I'd wanted to. Let's say y, let's write y as a sum on components yq times E hat Q now without the star. If I do that, then the Y sub Q is given by E hat sub Q complex conjugated dotted into Y. And so both these expansions are possible, and actually they're both useful, but the one that I want to use for the upcoming lectures is the first one. In fact, that's all we'll use for this course. Let's just take the first one because it turns out it's the one that works the best for the applications we want. All right. So that's basically the story of the spherical basis, what it is, and some of its basic properties. Now, I want to tell you something about what this is good for, and I probably won't have time to complete this. But let's take a one electron atom, which could be hydrogen or it could be one of the alkalis in the one electron model. It won't matter. And it's got two energy levels. Let's write them like this. And they have quantum numbers n, l, and m, and n prime, l prime, and m prime, like so. And let's talk about a radiated transition. So a photon is emitted going from the upper level into the lower level. So the unprimed ones is the initial one, and the primed ones are the final ones, final state. Now, it is shown in the theory of emission and absorption of radiation that the transition rate is proportional to the square of a matrix element, in which the matrix element in question is given by the matrix element connecting the initial and final states n, l, m on one side, and in the middle we have the position operator of the single electron, and n prime, l prime, m prime on the other side. We'll justify this later on in the course, and next semester we'll go into in some detail, but for right now, let's just accept that this is the matrix element in question. You probably saw this in your undergraduate course anyway. Now, the energies of these two levels are determined only by the N and L quantum numbers and are independent of the magnetic quantum numbers for the reasons I've just been explaining at some length. And so what that means is, but since the energies don't depend on the M's, that means that each of these so-called levels are actually degenerate levels, 2L plus 1 above and 2L prime plus 1 fold degenerate below. So you're really talking about transitions from one set of degenerate levels to another. The energy difference between the differences between those levels is the same for all possible transitions because the energies don't depend on the magnetic quantum numbers. They only depend on the N and L. So the energy difference is E sub NL minus E sub N prime L prime. That's going to be the energy of the emitted photon. So what we need to do to study this transition is we need to find these matrix elements for fixed values of N and L, and N prime and L prime, which give us the levels in question. But for all possible values of M, of which there's 2L plus 1, all possible values of M prime, of which there's 2L prime plus 1, and all three components of X. So that means there's 3 times 2L plus 1 times 2L prime plus 1 matrix elements that have to be evaluated to get the intensity of the spectral line. If we were talking, for example, about the 3D to 2P transition in hydrogen or in an alkali atom, this has got 5 levels, this has got 3 levels. So you're talking about 5 times 3 times 3, which is equal to 45. There would be 45 matrix elements to evaluate here. Looks like a big job. Okay, now, the spherical basis comes to our rescue. Instead of writing the components of X in Cartesian components, let's write it in spherical components. Let's write XQ is equal to the E hat sub Q dotted into X vector, like so. That doesn't change the number of components, but it simplifies some things, as I'll show you now. What we now do is make some observations. We look at a table of YLM. So if I look at Y11 and write it out explicitly, it's the square root of 3 over 4 pi. There's a minus sign here. It's a sine theta times e to the I phi. If we now multiply this by the radius r on both sides, I'll put the r here like this. R sine theta e to the I phi. Excuse me. This is divided by 8 pi here. R sine theta e to the I phi is the same thing as x plus iy. So this can be written this way as the square root of 3 over 4 pi times the quantity minus x plus iy divided by the square root of 2. Likewise, if you take r times y10, you'll find it's equal to the square root of 3 over 4 pi times z, which is r cosine theta. Get r cosine theta in here, you see, square root of 3 over 4 pi. And r times y1 minus 1 is equal to the square root of 3 over 4 pi times the quantity x minus iy divided by the square root of 2. And so by inspection of the YLMs, what we see is that there's a relation between the spherical components of the position vector of the electron and the 3 spherical harmonics. And the relation is this, is that r times y1q of theta and phi is equal to the square root of 3 over 4 pi times e hat q dotted into the position vector x, which is equal to the square root of 3 over 4 pi times what I'm calling x sub q. All right. And this then we will use this, plug this into the matrix element and play games with this matrix element. I'm out of time tonight, but that's going to be the first item on the agenda on Thursday evening, is to work through that. And we'll get to find out what the spherical basis is good for and also what the 3YLM theorem is good for. Somebody was asking about that earlier, and I'll show you an application of that. All right, are there any questions about this?
So the rate depends on the magnetic quantum number?
The rate, what you're probably interested in spectroscopically is the intensity of the spectral line. But you see, you have transitions. I mean, normally the excited state is going to, you won't have just one magnetic substate excited. It's likely to be all of them, with different probabilities. certainly if it's in thermal equilibrium or something, that's going to be the case. So what's going to happen, what the atom is going to do is it's going to make transitions from each of the upper M levels to each of the lower M levels. So you get all combinations of M and M prime, you see.
Why do the probabilities depend on the M in this case if the energy doesn't?
It's a good question. They do, and it has to do with the orientation. I mean, so there's further issues as well. The photon comes off of the polarization, and the polarization, so the probabilities depend on the polarization, and that's got a direction, just like the M's are indicating directions as well. So if I fix the polarization of the outgoing photon, well, let me put it this way, is that for if I took two definite M and M prime values, then the transition probability depends on the polarization of the photon. Or to turn it around, if I took a fixed polarization of the photon, then the probability depends on the M values, because it's related to the orientation of the atom, you see.
Mm-hmm.
The polarization of the photon gives you the orientation of the photon. I think that's the simplest explanation.
Okay. Why does the polarization of the photon have to be fixed, though?
It doesn't. The photon is going to be emitted in a variety of different polarizations.
Okay.
With probabilities for different polarizations.
Okay. I think I see.
Okay.
All right. Thank you.
We'll go through this in considerable detail next semester. You'll see how it all works out. It's actually a very pretty theory. We have to quantize the electromagnetic field first, though, before we do that. Okay, any other questions? All right, if there's no more questions, then thank you for everything tonight. And I will stop screen share and then stop recording.